Hello everyone, I'm Danny. This video is for the group project in the course MATH7502. Our topic is signal processing. In this video, I will introduce some main content of our topic, and the code is programmed in Julia, shown in a Jupyter notebook. The first part is the VMS 7.4. Well, in general, the convolution is a mathematical operation on two functions to produce a third function that expresses how the shape of one is multiplied by the other. Let's start with the vector convolution. This function is to calculate the convolution of two vectors a and b. And then let's say example, the time series smoothing. Here I use a piece of ECG signal. This is a time series and can be seen as a first vector. And the kernel here is the second vector. I define like this is an average kernel. And the result is like this. The orange one is the result is kind of being smoothed. And then let's say the two-dimensional convolution. Just a similar definition. This function is to calculate the convolution of a matrix A and B. And let's still see an example. We first log the image like this. This is the first matrix. And then I define the kernel like this, which is a 5 times 5 average kernel. This is the second matrix. Then we calculate the convolution of these two matrices, we can get the result. We can see the image is blurred because here we use the average kernel. The second part is from the LAFD 4.1 Fourier transforms. Let's start with the discrete Fourier transforms. This function is to build n times n Fourier matrix F. It contains the powers of this omega, is defined here. And similarly, we can generate a DFT matrix omega. It contains powers of this omega, is defined here. Then let's see an example. Here I still use the ECG signal, but intercept one period is 200 lengths. And then first we can build the Fourier matrix F and O DFT matrix omega with the same length 200. And then the omega times the signal F will produce the discrete Fourier coefficient C. This is also known as a discrete Fourier transform. We can get the result like this. And then the Fourier matrix F times C will bring back the signal F. This is also known as the inverse Fourier transform. And that's the result we can get. In this example, we didn't do any processing of the signal. We just have the Fourier transform and the inverse transform. So we just get back the original signal. Then let's see the fast Fourier transform, FFT. FFT is to get a faster Fourier transform. The key idea is to connect the Fourier matrix F with a half-size Fourier matrix. And as definition, it has three transforms. And in our Julia, we have three functions to get the three transforms or matrices. The first is a combination matrix. It combines the identity matrix with the diagonal matrix. And the second is a half-size transforms. And the third is an even-odd permutation. And let's see an example. Here we calculate the first step of FFT for the size 1024. And result is like this. We want to see if the result is same with the DFT we introduced above. This is the DFT result. And we simply calculate the difference between these two results, we get zeros. So the first step of FFT is equal to the DFT. And if we keep the recursion, we can calculate the full FFT. It means we separate the 1024 until the size of 2. This function is to calculate the full FFT. And similarly, we want to test if it has the same result with DFT. And we simply calculate the difference between these two results, and we also get zeros. It means the full FFT has the same result with DFT. The third part is from the LAFD 4.2. That first is the cyclic convolution. These two functions is to generate the shift matrix and the circulant matrix. And the cyclic convolution of vector A and B is defined like this. We first generate the circulant matrix for them, and then multiply these two matrices, and the result is the first row of the multiplication. And let's see an example of these two vectors C and D. The result is like this. And then let's see the convolution rule. It is a fundamental identity of signal processing. The left-hand side says we first calculate the cyclic convolution of vector C and D, and then calculate the Fourier transform. And then the right-hand side says we first respectively calculate the Fourier transform for C and D, and then multiply FC times FD component by component. They are the same. And say the same example with vector C and vector D. This is the left-hand result, and this is the right-hand result. They are the same. So that's the convolution rule. And that's all I want to introduce in my video, and thank you for watching.